Right. So this is we are into our week 5. So let's look at the agenda. So before we do anything, I'm going to tell you about term test 2, term test 1. So term test 1 will be on June 6th, and it's going to start at 1900, and we are going to go into 2130. So 2 hours 30 minutes. There'll be 3 questions. And the questions will be very similar. Okay, not exactly the same, but similar to homework 1, homework 2, and homework 3. And from the examples taught in class. Okay, so you need to know all this.
Sorry, Eugene, does this class also being included?
No, today's lecture is not included, okay, in the term test. Today's a new topic. Then we have, let me very soft at my end. There's something else. So the room is ABB. If I go into Avenue, I put the announcement on Avenue already. I just want to check. Yeah, ABB 136. And if you look into the ABB 136, I also posted the formula sheet. So these are the formulas that you'll be getting. I don't expect you all to memorize, but these are the formulas that you'll be getting. Okay, so ABB. Okay, ABB 136. Okay, so 2.5 hours, 3 questions. So the agenda today is I'm going to do an introduction to combined loading. Okay, and then we are going to go into an introduction also of shearing stresses. So shearing stresses, I always say in class, is one of the most difficult chapter. Okay, and I'll teach this for about 3 weeks, at least 3 weeks. Okay, so shearing stress is one of the worst in structure analysis or engineering mechanics. Okay, so let's look at combined loading. We have done a bit of combined loading on our previous example. Okay, so let's look at combined loading. So under combined loading, I want to emphasize what I've taught. So when we were doing this example before, okay, it is this aspect that we want to look at. Okay, so I will copy this from notes. Okay, so we wrote this. When the applied force is parallel to the centroid, the perpendicular distance to calculate the moment is between the applied force and the centroid. And then we also did this, okay. Let me make sure that I just copy. Okay, you will do everything is fine. And then there's a statement that we make is when the applied force, right? We had this when the applied force is perpendicular to the centroid. The perpendicular distance to calculate the moment is between the applied force to the point or surface of failure. So two very different approach. Okay. So what we are trying to do is we are in this chapter or in this topic over here, we are going to identify and calculate axial force. We also want to determine the shear force. We also want to determine the bending moment. And we also want to identify the torque. Okay. So if I were to have a transformation in 3D, okay, or if I have a shaft, let's draw the transformation first. So this is X, Y, and Z. And my shaft is oriented in this direction. And then we want to identify the element. Okay, so element is any point of interest. Okay, so this is our element. So over here, this is our element. So when we call an element is basically the location where stresses will be formulated. Okay, usually is the failure point, or usually the point of failure. But for now, we don't have that experience to identify exactly where first, so we have to do more of it. Okay. So once that is your element, immediately, like before, you draw your geometric centroid or geometric axis. Okay. So this is your geometric axis relative to the centroid. Okay. So this structure can have stresses applied or forces applied in this direction. Okay. So Px. So Px over here is our axial force, and it will generate forces, stresses in the x direction. And the formula to apply is Px over A. Okay. And where A is the cross-sectional area. Okay. And likewise, we can have forces coming down. Oh, sorry, wrong color. We can have also forces coming down. And this is your Vy, and forces going in this direction, which is your Vz. Okay. So I'm going to, so Vy and Vz is the shear force applied, okay, the shear force in the y direction. And the formula we're going to put in to calculate. So shear force, it will generate a shear stress, which is equal to Vy over Izz Qz over T. Okay. So I will define, so you know what is Vy. So Qz, which you don't know, which is what we are going to learn in the next major chapter, is shearing stress. So Qz is the first moment of area about the z-axis. We know what is Izz. Okay. Izz is the second moment of area. About the z-axis. And then you have T is what we call our thickness of the material or of the structure. Okay. So that's what we use Vy for. We are there to calculate the shear stress. And also we have Vz, okay, which is the shear stress or shear force in the z direction. And the formula to calculate, we also still calculating shear stress, which is equal to Vz over Iyy Qy over T. Yeah, as you can see that. Now the shear force, right, Vy and Vz relative to the element, they have a perpendicular distance known as L. Okay, there's a perpendicular distance. So as you can see, the forces are perpendicular, right, to the centroid. So you take to the element, right? The perpendicular distance is to the element. So over here, you realize that we have mz, right? What we can see is from here, the Vy will also cause a moment about z. So mz is equal to mz will be equal to Vy multiplied by L. Okay, so you know, so mz is moment about the z-axis. So in this case, given a moment, what we want to calculate is using the formula, we're going to calculate stress in the x direction is equal to mz over Izz multiplied by y. Okay. It's important to see that in moment, if it's mz, right? If it's mz, right, we do Izz. Whereas in shear, if it's Vz, we use what? Iyy. If it's Vy, we use Izz. Okay, so there's a trend in the formula. And then I don't think I need to define what these values are, or C or Y. Okay, so it might be, so Y is the furthest distance from the centroid.